Neutron stars are some of the most fascinating and extreme objects in the universe. They are born from the violent deaths of massive stars, and what remains after the explosion is a stellar core so dense that it packs the mass of the Sun into a sphere only about 12 miles, 20 kilometers, wide. To put that in perspective, a teaspoon of neutron star material would weigh as much as a mountain. These compact, dense objects have unique properties that push the boundaries of our understanding of physics. In this short video, we'll explore what neutron stars are, how they form, why they are so dense, and the mysteries they still hold. A neutron star is a collapsed core of a massive star left behind after the star explodes in a supernova. This happens to stars that are much larger than the Sun, typically 8 to 20 times its mass. When these stars run out of nuclear fuel, they can no longer support the force of gravity pressing inward. The outer layers of the star are blown away in a supernova explosion, while the core collapses under gravity to form a neutron star. Neutron stars are incredibly small by stellar standards, usually around 12 to 15 miles, 20 to 25 kilometers in diameter, but they are unimaginably dense. A neutron star contains about 1.4 times the mass of the Sun, squeezed into a volume with a radius about the size of a city. This gives them a density far greater than anything we experience on Earth. The extreme density of a neutron star comes from the nature of its collapse. When the core of a star collapses, protons and electrons are crushed together so tightly that they combine to form neutrons. The entire star becomes a solid mass of neutrons, held together by gravity and supported by neutron degeneracy pressure, a quantum mechanical force that prevents neutrons from being crushed any further. This means a neutron star is essentially one gigantic atomic nucleus. Its density is extraordinary, about 10 to the power of 17 kilograms per cubic meter. That's equivalent to compressing all of humanity into the volume of a sugar cube. To give a more concrete example, imagine a neutron star's density like this. If you took Mount Everest and crushed it down to the size of a marble, that would be a good approximation of the density of a neutron star. The formation of a neutron star is part of the life cycle of a massive star. Here's a step-by-step look at how this process happens. 1. A massive star's life. A star that is at least 8 times more massive than the Sun begins its life by fusing hydrogen into helium in its core. Over time, it burns through its nuclear fuel, fusing progressively heavier elements like carbon and oxygen. 2. Supernova explosion. When the star's core runs out of fuel and can no longer sustain nuclear fusion, it can no longer fight against gravity. The core collapses, and the outer layers of the star are ejected in a massive explosion called a supernova. 3. Core collapse. As the core collapses, protons and electrons are squeezed together, turning into neutrons. The neutron star is born when the collapse is halted by neutron degeneracy pressure, the force that prevents neutrons from being squeezed any further. 4. The neutron star. What's left is a small, incredibly dense object made almost entirely of neutrons. The neutron star will cool and spin rapidly, but its density will remain constant, making it one of the densest objects in the universe. Neutron stars are not just dense. They also have other unique properties that make them some of the most fascinating objects in astrophysics. 1. Incredible gravity. The gravitational force on the surface of a neutron star is about 2 billion times stronger than Earth's gravity. If you could stand on a neutron star, which you can't, the gravity would crush you instantly. 2. Rapid rotation. Neutron stars often spin incredibly fast. Some rotate hundreds of times per second, which happens because the original star's angular momentum is conserved as it collapses. These rapidly spinning neutron stars are called pulsars because they emit beams of electromagnetic radiation, which sweep across space like the beam of a lighthouse. 3. Powerful magnetic fields. Neutron stars have some of the most intense magnetic fields in the universe, trillions of times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have magnetic fields so strong that they can distort atomic structures and even affect the behavior of space around them. For pulsars. Pulsars are a type of neutron star that emits beams of radiation from their magnetic poles. As they spin, these beams sweep across Earth like a lighthouse, producing regular pulses of radiation. Pulsars were first discovered in 1967, and they have become important tools for studying extreme physics, including the warping of space-time caused by gravity. Despite decades of study, neutron stars still hold many mysteries. Some of the key questions researchers are exploring include: 1. What happens inside a neutron star? The extreme conditions inside neutron stars push the limits of our understanding of physics. The core of a neutron star might contain strange forms of matter, such as quark-gluon plasma, where protons and neutrons break down into their constituent quarks. But the exact nature of this dense core is still unknown, as we don't have the technology to directly observe it. 2. Neutron star collisions. When two neutron stars collide, they create some of the most violent and energetic events in the universe, known as kilonovae. These collisions produce gravitational waves, ripples in space-time, and can also forge heavy elements like gold and platinum. Observing these collisions helps scientists understand more about neutron stars and test theories of gravity and nuclear physics. 3. The maximum mass of a neutron star. While neutron stars are incredibly dense, there's a limit to how much mass they can hold before collapsing into a black hole. This maximum mass is still an open question in astrophysics, and discovering more neutron stars close to this limit could provide clues about the ultimate fate of massive stars. 4. Magnetars and their explosive power. Magnetars, the most magnetic neutron stars, are known to produce bursts of energy called soft gamma ray repeaters that are so powerful they can affect satellites on Earth. However, the exact mechanisms behind these massive energy releases are still not fully understood. Neutron stars represent some of the most extreme objects in the cosmos, pushing the boundaries of our understanding of matter, gravity, and the life cycles of stars. Their incredible density, rapid rotation, and intense magnetic fields make them both fascinating and mysterious. By studying neutron stars, astronomers hope to unlock new insights into the fundamental laws of physics, the behavior of matter under extreme conditions, and the ultimate fate of massive stars. These mysterious objects remain a key area of research in modern astrophysics, and their secrets are sure to keep scientists intrigued for decades to come. Thanks for watching.